My name is Patel Swar, and today I am going to present my project of microprocessor and computer organization, that is on how microprocessor and operating systems are integrated and how they work simultaneously. Let's begin. So today we are going to cover these topics. They are introduction to microprocessors, evolution of microprocessors, components of a microprocessor, how a microprocessor works, introduction to operating systems, types of operating systems, key functions of an operating system, process management, memory management, file system management, device management, integration of microprocessors and operating systems, boot process, interrupts and their role, multitasking and multithreading, real world example like Windows OS and Intel processors, challenges in integration, future trends. Introduction to microprocessors. A microprocessor is basically a controlling unit of a microcomputer fabricated on a small chip capable of performing ALU operations and communicating with the other devices connected to it via different buses and cables, and transferring the data and instructions through each and every part of the microprocessor. Here's the importance of microprocessor. Microprocessors nowadays have revolutionized technology powering everything from computers to smartphones. Their increasing power has led to advancement in fields like artificial intelligence and machine learning. They have enabled the creation of smaller, faster, and more efficient devices, transforming the way we live, work, and interact with the world. Microprocessors have become the foundation of modern technology, driving innovation and progress in countless industries. So basically, microprocessors have today taken place in each and every part of our modern life. Evolution of microprocessors. The evolution of microprocessors started early, dating back to the 1970s, when the Intel 4004 8080, when the microprocessors were newly launched into the commercial market. Personal computer era 1980s. Intel 8086, 80286, 80386, where the architectures were enhanced to improve the memory management, multitasking, and efficient processing. The rise of Pentium, that is 1990s. Intel Pentium, Pentium 2, 3, and 4, the main revolutionary era before the modern era in which companies extended their boundaries to next extent to make the microprocessors more efficient. Now, currently, the modern era, 2000s to present, multi-core processors, mobile processors, specialized processors, which are nowadays used also for big tasks. Nowadays, the microprocessors are used in each and every devices, just like our computers, laptops, phones, even our headphones and that type of devices. Components of a microprocessor. Control unit, the brain of the microprocessor, responsible for fetching, decoding, and executing instructions and coordinating the overall operation. Arithmetic and logic unit, which performs arithmetic and logical operations on data and handles the actual computation of results. Registers, high speed storage elements for temporary data used to store instructions, data, and intermediate results. Clock generates pulses to synchronize the microprocessor, determining its speed or frequency. Interconnect, network of wires interconnecting components, allowing data to flow between the different parts of the microprocessor. Memory stores instruction, data, and results divided into read-only memory, that is ROM, for permanent data, and random access memory, that is RAM, for temporary data. How a microprocessor works. So basically, microprocessor has the most basic five processes, that is fetch, decode, execute, store, repeat. In fetch, the microprocessor fetches the instruction from the memory using the program counter to keep track of the upcoming instructions to be executed. In the decode phase, the instruction is decoded to determine the operation to be performed and the operands to be used. This involves breaking down the instruction into a series of micro instructions that can be executed by the control unit. Execute. The ALU performs specified operation on the data using the registers to hold the operands and the result. The ALU can perform various arithmetic and logical operations such as addition, subtraction, multiplication, division, and, or, and not. In the store phase, the result of the operation is stored back in the memory or any of the registers that we want to store our data in. This cycle continues to repeat till the last instruction is completed. Introduction to operating systems. Operating system is basically a software program that manages a computer's hardware, software, and data. It acts as an intermediary between the hardware and the user, providing a platform for applications to run and interact with the system. So basically, operating system is like integration, is like supporting a base for connecting the microprocessor with the software applications that we are able to use right now on our devices. Importance of operating systems: resource management that allocates and manages system resources, user interface, application execution, security, the most important aspect that protects the system from unauthorized access and unauthorized upcoming threats to our data and our devices. Compatibility. The OS also ensures compatibility between hardware and software. Performance optimization. The types of operating systems that are based on functionality are real-time OS for immediate responses in industrial control, like any of the industrial machines that are used for the real-time processes, like a chemical factory having different machineries for the boiling point, also use an OS. The multitasking OS, which handles multiple tasks simultaneously, which are like Windows and Mac OS, which we currently use for our different purposes. Single user OS for one user. Example, embedded systems. These are the single users OS which were used for simple personal computers. The multi-user OS for multiple users. For example, a server handling multiple requests from multiple users and giving them their desired outputs based on target use cases. Desktop OS for personal computers, server OS, embedded OS, mobile OS for smartphones and tablets, that is Android and iOS. Key functions of an operating system: resource management, which allocates and manages system resources, CPU, memory, input output. Process management creates, manages and terminates processes. Memory management allocates and deallocates memory to processes. File system management organizes and manages files and directories. IO management handles input or output operations between devices and the system. Security protects the system from unauthorized access and attacks. Networking enables communication between devices on a network. User interface provides a user-friendly interface for interacting with the system. Application execution, which executes the application and provides necessary services to the user. Process management, process creation and scheduling. The OS creates them and manages the process. The scheduler allocates CPU time to process based on algorithms like round robin, priority, and many more. Microprocessor executes instructions of processes based on OS scheduling. Multitasking. OS handles multitasking, time slicing, and preemptive scheduling. Microprocessor switches between processes rapidly to simulate the simultaneous execution and Through the multitasking, a user may feel like he is paid full attention by the OS or the microprocessor, and it may enhance the working of the microprocessor and OS. Context switching. OS saves the state of the current process and loads the state of the next process. Microprocessor resumes execution of the newly scheduled process. Interrupt handling. Microprocessor holds current execution to handle interrupts like an event occurring in the hardware or a software where an interrupt may occur, and this halts the current execution of any program that is being right now executed in the microprocessor. OS processes the interrupt and sends the instruction to the microprocessor to resume or switch task, or it may uh, give it to the routine that is to be called while using the interrupts. Memory and resource management. OS allocates memory using virtual memory and ensures no process exceeds its bounds. Microprocessor uses its memory addresses assigned by OS to execute process instruction efficiently. So basically this point is for the memory and resource management, which is a big issue nowadays. Memory management. Memory allocation. OS allocates physical and virtual memory to processes. Microprocessor accesses memory addresses provided by OS. Virtual memory. OS uses paging or segmentation to extend memory beyond physical RAM. Microprocessor using MMU, memory management unit, to translate virtual addresses to physical addresses. Here, in this concept, the OS creates a part or a segment in the secondary memory and uses that part as a part of its extended RAM, and this enhances the what we can say fetching and continuous faster management of the different multiple tasks. Microprocessor uses MMU, memory management unit, to fetch those virtual addresses and execute them into the various physical addresses and store it on the physical devices. Memory protection. OS enforces protection mechanisms to prevent one process from accessing another memory. Swapping. OS swaps inactive processes to disks when memory is full. Microprocessor manages swapped in process when they return to active memory. Cache management. Microprocessor uses cache, that is level 1, level 2, level 3, for faster access to frequently used data. OS optimizes memory used to ensure efficient cache utilization. File system management. File organization. OS organizes data in directories and files, managing file metadata, that is different type of data, part of the data. Microprocessor executes file system instruction as directed by the operating system. File access. OS controls files access via the system calls, that is read operation, write operation. Microprocessor executes these system calls interacting with the storage devices. Storage management. OS allocates and deallocates disk space for files. Microprocessor retrieves and stores data at locations specified by the operating system. File protection and security. OS enforces access control to ensure data integrity and security. Microprocessor handles security enforcement by executing privileged operations under the OS control. Buffering and caching. OS manages file buffering to optimize the input-output operations. Microprocessor leverages cache to speed up the file read or write processes. Device management. Device drivers. OS uses device drivers as an intermediaries between hardware and software. Microprocessor executes driver instruction to communicate with the devices such as printer, keyboard. I/O management. OS schedules and prioritize the I/O operations from the devices like mouse, keyboard, scanner, etc., and gives the following output to the monitor, printer, etc. Microprocessor handles input-output interrupts, pausing processes to manage device requests, interrupt handling, buffering and spooling, plug and play. The interrupt handling we'll discuss in the next slide. Buffering and spooling. The buffering is used by OS to temporarily store the data during I/O operations and spooling for devices like printers. Microprocessor executes buffer data transfer for smoother device interaction. Plug and play. OS manages automatic detection and configuration of new devices. Microprocessor assists by executing the PNP, that is plug and play routines initiated by the OS. Integration of microprocessor and operating system. Process creation and termination. The OS is responsible for creating new processes, that is using system calls like fork in Unix or Linux, and terminating them once they complete. Thread management. The OS can break down processes into threads for more efficient multitasking. The microprocessor uses multiple threads, often within the same processes, to increase parallel execution. Cache management. The microprocessor uses levels of cache memory to store frequently accessed data. File system interaction. The OS manages file storage, reading and writing through the file system. The microprocessor processes file system instruction by accessing storage devices like HDD, SSD based on the commands from the OS. Resource allocation. The OS manages system resources like CPU, memory, input-output devices to ensure each process has the resources it needs. Deadlock prevention. The OS employs deadlock detection and prevention techniques like resource ordering or priority inheritance to prevent system hangs. The microprocessor follows these algorithms to ensure no processor gets stuck waiting for resources. System calls and API. The OS provides a set of system calls that allow applications to request services like file input-output or memory allocation. The microprocessor executes the system calls interfacing between software and hardware. Here, in this concept, the OS provides few basic system calls that are needed to be followed by the application for different purposes like input-output operations in the memory. Virtualization. The OS can relate virtual machines or containers that allow multiple OS instances to run on a single microprocessor. The microprocessor efficiently switches between these virtualized environments managed by a hypervisor. Error handling and recovery. The OS detects and handles errors and takes corrective actions such as terminating faulty processes or restarting drivers. The microprocessor triggers hardware interrupts or exceptions which the OS uses to initiate error recovery and routing. Power and thermal management. The OS monitors and controls the power system's power usage and temperature to optimize the performance. Multi-core processing. The OS schedules tasks across multiple cores in multi-core processors to maximum parallelism. The microprocessor with multiple cores executes tasks concurrently, increasing overall system performance. DMA, that is direct memory access. The OS manages direct memory access for the data direct transfer between memory and I/O devices without involving the CPU. Here, in the direct memory access concept, there is a DMA chip that does not disturb the main CPU for input output operations and their requests. The microprocessor oversees the DMA controller, allowing efficient data transfer and freeing up CPU resources for the other tasks. Boot processes. Post subroutine. This subroutine is initiated we turn on our computer, and using this the computer ensures that everything in the computer is right now working correctly. Loading the bootloader execution, loading the operating system, which loads the OS kernel into the memory and initializes it. Kernel initialization, system initialization, user login and interface, which we are shown at the very first page when we are supposed to log in and enter our password and enter into the desktop of our of our computer. System ready for use. Interrupts and their role. Types of interrupts. Hardware interrupts. An interrupt generated by an external device like a keyboard or a mouse. We can say that hardware interrupts are like generated when there is an error in any of our external device like mouse, keyboard, and they are not working properly. Software interrupt. And software interrupt is that is caused by an instruction in a program like an exception or error or system calls. Interrupt vectoring jumps to the appropriate interrupt handler, that is jumping branching the microprocessor to the particular subroutine and calling the subroutine to handle the interrupt caused. OS responsibilities. Manages interrupt handlers and prioritizes requests. Enables multitasking and preemption of running processes. Its benefits are asynchronous processing that allows CPU to handle other tasks, enhances efficiency, responsiveness, and error handling. Multitasking and multithreading. Multitasking. Definition. That is, ability to run multiple processes simultaneously, which allows users to perform various tasks without waiting for one task to finish before starting another. The OS role in it is to manage the process scheduling, allocate CPU time using algorithms like round robin, priority. The OS uses scheduling algorithms to ensure fair CPU time distribution and among processes to meet system responsiveness of requirements. The microprocessor's role here is to perform context switching between processes, allowing rapid task switching. The microprocessor saves the state of current processes and loads the state of next process, enabling quick instructions. Multithreading. Here, the ability to run multiple threads within a single process concurrently, which allows a single application to perform tasks like handling user input and background operations simultaneously. The role of OS is to create and manage threads, optimizing the resource usage and enabling parallel execution. The OS handles thread lifecycle management, including creation, synchronization, and termination of threads to maximize CPU utilization. Microprocessor role executes threads in parallel in multi-core systems, increasing efficiency and responsiveness. The real-world example of it is Windows OS and Intel processors. As we all know, the most famous operating system that most of us people use, that is Windows, and the widely used processors in each and every computer CPUs that are Intel. Optimized performance. The Windows and Intel are the big giants that are integrated in such a way that they work with each other and give the give the best performance to the user. Energy efficiency, security enhancement, software compatibility, AI and machine learning. Intel's support for AI acceleration combined with Windows AI feature boost applications that rely on deep learning and neural networks. Challenges in integration, compatibility issues. The biggest issue is that the particular OS is compatible with the microprocessor or not. Driver support, developing and maintaining drivers for the developers is a is a big is a big challenge when it comes to developing the drivers that support the integration between hardware and the Intel hardware and Windows OS. Performance optimization, security vulnerabilities. The most important aspect is that the hardware level security flaws in Intel processors such as Meltdown and Spectre require OS level patches from Windows, sometimes leading to reduced system performance. Software ecosystem adoption. Application must be optimized to take full advantage of new Intel processor capabilities, which can lag behind the release of new hardware and OS updates. The future trends that may be in the OS and microprocessors integration, that is AI and machine learning. As we all know that nowadays the AI and machine learning has got a boost due to the upcoming generation, due to the new generation of OS and the new generation of the current microprocessors that are more efficient in performing different tasks. Quantum computing, as Intel devices in quantum computing future Windows OS versions may incorporate support for quantum architectures, leading to groundbreaking performance improvements, enhanced security features which strengthens the hardware-based security measures such as Intel's hardware shield integrated with Windows security protocols to combat advanced cyber threats. Edge computing, energy efficiency and sustainability. Innovations focused on reducing power consumption through smarter power management and leveraging Intel's energy efficient technologies, enhancing the battery life in mobile devices. Thank you, everyone.